Okay, let's carry on with that. So let's clear some space here. Let's get this right. So I'm just going to shift this stuff up here. Okay, so that's the first correction that we want to apply there. And if you recall the derivation for the concentration gradient across the particle, namely to give us the internal effectiveness factor, then you can see how to correct for CAS. So remember that the average concentration inside the particle, that's equal to the internal effectiveness factor times the concentration on the surface of that particle. So this parameter we derived in terms of a mass balance across that particle. So I will release a separate video for the mass transfer, solving the reaction diffusion equation to get to the concentration profile across the particle. And once you have that, you can average out that solution to get to the true average for concentration there. So anyway, we summarize that in terms of this parameter, the internal effectiveness factor, so that's there. And then you see here, this refers to the concentration across that external film. So we can call this the external effectiveness factor. So eta external times Ca, that's equal to CAS. Right, so we can put all this together. You can see here the average concentration of Ca in the particle, that's equal to that. And we can just replace this for CAS, so we can rewrite this as eta external times Ca. And now we actually have the result that we were looking for. We have related the concentration in the bulk phase, so the concentration here, we've related that now to the concentration inside the particle, so the average concentration in that particle. So that's the relationship that we need, because now in our mole balance, right, let's just rewrite the mole balance here. We can say dCA dt is Ca in minus Ca over tau minus we had Ra double dashed times let's just write the constants here. We needed to multiply by the specific surface area and the mass of catalyst, and we had divided by the volume of the reactor. Right, so that's that was our overall mole balance. And then this Ra, now we can see Ra double dashed is equal to Ks times Ca, the average concentration, the concentration that's actually responsible for the reaction. So the reaction is happening here, so the relevant concentration is Ca over bar. So that's equal to Ks eta int times eta ext times Ca. Right, so when we replace for Ra double dashed in this equation, we now have an equation that's written just in terms of Ca. Right, you can see here specific surface area, mass of catalyst, volume of reactor. These things may all be constant in time. These things we also regard as constants. So when we put all this together in this equation, we eventually have Ca as basically the only unknown, and we can solve for the concentration in that reactor then. So let's try and put it all together. Let's do it on a separate layer. So we've got dCA dt is equal to Ca in minus Ca over tau minus Ks Ca eta int eta ext. So that's the area based rate, and we have to multiply that by SA times mcat divided by the volume of the reactor. And you can identify this as the bed density of catalyst particles, right? This is the mass of catalyst in the reactor. That's the volume of that reactor. So that's effectively the density of catalyst particles in that reactor. So anyway, let's just lump all these things together. Let's just group all of this as a set of constants. So let's just call all of that equal to K1. And let's say that this is at steady state, right? So we are feeding A in here. It's reacting, and we're getting some concentration of A out here. So there is a constant supply and withdrawal of A. So we can imagine that we will accomplish some steady state concentration of A in that reactor. So we may get a steady state in that reactor. Steady state. And so we can rewrite this equation in the following form. Let's go back to that color. So we can say here that Ca in minus Ca over tau minus K1 Ca is the balance that applies, and we can easily solve this equation for Ca. More effectively, we could rewrite this in terms of conversions. So in fact, let's just take one across here. Let's just rewrite it as Ca in minus Ca is equal to, let's just draw a line here, that's equal to K1 times tau times Ca in 1 minus x. Right, remember Ca we can always write as, we can rewrite this as Ca in times 1 minus x, where x is the conversion. So just the definition of conversion, of course, what we've used there is that Ca in minus Ca over Ca in, right, that's the conversion. So if we divide through here by Ca in, we are getting that, right? If we divide this by Ca in, and we divide that out, then we're getting here, this is nothing but the conversion. So that's conversion equals K1 tau times 1 minus x. Right, so that's a nice easy equation. You can just solve this for the conversion if you have the set of constants and the space-time of that reactor. So these K's, it's nothing but this, the kinetic rate constant, the effectiveness factor, specific surface area, mass of catalyst, volume of reactor, all of those things we will have as constants, so that defines that. Another way to say it is that if we want a certain conversion, let's say we want a nice high conversion like 90% or whatever it is, we can specify the conversion, we can specify the constant, and then we can work out what the space-time of that reactor should be. So if we know what space-time we want, let's say we know we want a space-time of tau, and we know that the reactor is being fed at V0. Oops. Right, we know space-time is V over V0. Then we can just use this to say the volume of that reactor should then be V0 times tau. Right, so that's basically a simple design variable. We can determine what the volume of that reactor should be in order to accomplish a particular conversion X.